A pulse of seismic energy rippled across the northeastern Pacific during the quiet hours of the morning, reminding coastal communities and scientists alike that one of North America's most closely watched tectonic regions never truly rests. Far offshore from Vancouver Island, an earthquake measuring magnitude 5.6 struck along the Sovanco Fracture Zone, approximately 208 kilometers, or about 129 miles, southwest of Port McNeill, Canada. According to seismic data, the earthquake occurred at 6:41 and 30 seconds Coordinated Universal Time on the 20th day of July, 2026, at a depth of approximately 10 kilometers, or about 6 miles below the seafloor. For many people, any earthquake occurring near the Pacific Northwest immediately raises a single question. Did Cascadia move? It is an understandable reaction. The Cascadia Subduction Zone has earned worldwide attention because it represents one of Earth's most powerful earthquake-producing systems. Memories of the colossal earthquake of the year 1700, reconstructed from Japanese tsunami records, indigenous oral histories, and geological evidence, continue to shape modern discussions about seismic hazards along the western coast of Canada and the United States. Yet the answer is more nuanced than a simple yes or no. The location of this latest earthquake immediately offers an important clue. Rather than occurring directly on the Cascadia megathrust, where the Juan de Fuca plate dives beneath the North American plate, the event originated along the Sovanco Fracture Zone, an offshore transform fault system that forms part of a much broader network of tectonic structures connecting spreading centers, oceanic plates, and fracture zones across the northeastern Pacific. To understand why this earthquake occurred and what it does and does not mean, it helps to picture the Pacific Ocean floor not as one continuous slab of rock, but as an immense mosaic of moving plates separated by ridges, faults, and fracture zones extending for thousands of kilometers beneath the sea. Although hidden beneath vast depths of water, these geological boundaries remain among the most dynamic places on Earth. Far offshore from Vancouver Island lies the Explorer region, one of the most geologically fascinating corners of North America. Here, the Pacific Plate, the Juan de Fuca Plate, and the smaller Explorer Plate interact through a remarkably intricate arrangement of spreading ridges, transform faults, and fractured crust. Unlike simpler plate boundaries where motion occurs along a single fault, this region resembles an interconnected web in which multiple structures continually accommodate Earth's slow but relentless tectonic motion. The Sovanco Fracture Zone occupies an important place within this network. Stretching across the northeastern Pacific, the Fracture Zone links segments of the Explorer Ridge with neighboring tectonic features. Although invisible beneath thousands of meters of seawater, it represents a long-lived zone of weakness within the oceanic lithosphere. Over millions of years, repeated tectonic movement has left its mark on the rocks, allowing stress to accumulate and eventually release through earthquakes. Unlike the giant thrust faults responsible for the world's most destructive megathrust earthquakes, transform faults primarily accommodate sideways motion. Massive blocks of oceanic crust slowly slide horizontally past one another. The movement is incredibly slow on a human timescale, measured in only a few centimeters, or roughly an inch or two per year. Yet over decades and centuries, stress steadily builds until friction can no longer hold the rocks together. When that stored energy finally overcomes resistance, the rocks abruptly slip. That sudden movement generates seismic waves racing outward through Earth's crust and into the surrounding ocean, where sensitive seismic stations record the event within seconds. A magnitude 5.6 earthquake represents a significant release of energy, although it falls well below the size associated with devastating regional disasters. Such earthquakes are capable of producing noticeable shaking over broad offshore areas, and may be detected by residents along portions of Vancouver Island, depending on local geology and distance from the epicenter. Because this earthquake occurred more than 200 kilometers offshore, much of its energy dissipated before reaching populated areas. Its offshore location also greatly reduced the likelihood of serious damage. Nevertheless, every earthquake occurring near the Pacific Northwest inevitably attracts close attention from seismologists. Every recorded event contributes another valuable piece to the evolving picture of tectonic activity along one of Earth's most complex plate boundaries. One reason the Sovanco Fracture Zone commands scientific interest is its relationship with the Explorer Plate. Many people have heard of the Juan de Fuca Plate, but fewer realize that immediately to its north lies the smaller Explorer Plate, a remnant of the once vast Farallon Plate that dominated the eastern Pacific millions of years ago. As the ancient Farallon Plate fragmented through time, several smaller plates emerged. Among them are the Juan de Fuca Plate, the Explorer Plate, and the Gorda Plate. Each continues moving independently while interacting with neighboring plates through an intricate combination of spreading, transform motion, and subduction. The Explorer Plate has long puzzled geologists. Unlike neighboring plates with relatively straightforward movement, the Explorer Plate exhibits signs of internal deformation. Rather than behaving as one perfectly rigid block, portions appear to experience distributed strain across multiple faults. This complexity creates an environment where earthquakes can occur across a variety of fault systems rather than being confined to a single plate boundary. The Sovanco Fracture Zone plays a major role in accommodating some of this tectonic adjustment. Repeated earthquakes over many decades indicate that stress continues to accumulate and release along this offshore boundary. Rather than representing an isolated feature, the fracture zone forms part of an active tectonic corridor extending across the northeastern Pacific. Modern marine geophysical surveys have revealed dramatic topography surrounding the fracture zone. Deep valleys, elongated scarps, offset volcanic ridges, and rugged seafloor landscapes testify to millions of years of tectonic displacement. These underwater landforms preserve the geological history of countless earthquakes occurring long before humans ever occupied the Pacific Northwest. Every major earthquake subtly reshapes portions of this submerged landscape. Most of those changes remain invisible beneath the ocean surface. Ships passing overhead notice nothing unusual. Fishing vessels continue operating. Commercial shipping lanes remain open. Far below, however, rocks have shifted by amounts ranging from a few centimeters to several meters during individual earthquakes, gradually sculpting the architecture of the ocean floor over immense spans of geological time. Modern seismology allows researchers to reconstruct these events with remarkable precision. Networks of seismic stations distributed throughout Western Canada, the United States, and the global monitoring system detect the arrival times of different seismic waves. Computers compare thousands of observations, calculating the earthquake's location, depth, and magnitude within minutes. Additional analysis often reveals the fault orientation responsible for the rupture. For transform earthquakes such as those commonly associated with fracture zones, focal mechanism solutions frequently indicate predominantly strike-slip motion. That means the rocks primarily move sideways rather than one plate being thrust upward over another. This distinction matters enormously when assessing tsunami potential. The largest tsunamis usually develop when massive sections of the seafloor experience significant vertical displacement, abruptly lifting or lowering the overlying ocean. Strike-slip earthquakes generally produce much smaller vertical movement. Although exceptions exist, especially where complex fault geometry introduces localized uplift or subsidence, transform earthquakes rarely generate the enormous tsunamis associated with giant megathrust events. Consequently, a magnitude 5.6 strike-slip earthquake on the Sovanco Fracture Zone typically presents a far lower tsunami hazard than an earthquake of similar size occurring directly along a major thrust fault. That does not diminish its scientific significance. Quite the opposite. Every earthquake offers researchers an opportunity to better understand the mechanics governing plate boundaries. One persistent question involves the relationship between offshore fracture zone earthquakes and the Cascadia Subduction Zone itself. Public attention often assumes that any earthquake near Vancouver Island indicates movement on Cascadia. Reality proves considerably more complicated. The Cascadia megathrust marks the boundary where the Juan de Fuca Plate descends beneath the North American Plate. This immense fault stretches from Northern California through Oregon and Washington to Vancouver Island. It is capable of producing earthquakes approaching magnitude 9. The Sovanco Fracture Zone, by contrast, lies within the oceanic plate system west of the subduction boundary. Although both belong to the same regional tectonic environment, they represent different structures, accommodating different types of plate motion. An earthquake occurring on one does not automatically mean the other has ruptured. That distinction is essential. Earth's crust constantly redistributes stress. Movement along one fault can produce subtle stress changes on neighboring faults, but such interactions usually diminish rapidly with distance. Scientists evaluate these relationships carefully using sophisticated computer models capable of estimating Coulomb stress changes across regional fault networks. For moderate earthquakes like this one, those stress changes generally remain quite small over the distances separating the Sovanco Fracture Zone from the principal locked portions of Cascadia. In other words, while both systems belong to the same tectonic neighborhood, a magnitude 5.6 fracture zone earthquake does not provide evidence that the Cascadia megathrust itself has begun rupturing, nor does it necessarily increase or decrease the probability of a future Great Cascadia earthquake in any meaningful way. The long-term earthquake cycle governing Cascadia continues according to processes unfolding over centuries. Continuous global positioning system measurements collected across western North America reveal that portions of the Juan de Fuca Plate remain strongly locked against the North American Plate. Instead of sliding smoothly, the plates resist motion. Each year, tectonic convergence slowly stores elastic strain within the surrounding crust. That process continues regardless of whether moderate offshore earthquakes occur elsewhere in the regional plate system. Eventually, perhaps decades or centuries from now, enough stress will accumulate for Cascadia to rupture again. Exactly when remains unknown. No currently available scientific method can determine the precise timing of that future earthquake. This uncertainty often fuels speculation following moderate offshore earthquakes. Every noticeable tremor prompts renewed public discussion regarding whether a larger event has become imminent. Scientific evidence consistently advises caution. Earthquake prediction remains beyond present capability. Researchers can estimate long-term probabilities, identify hazardous faults, and monitor ongoing deformation, but they cannot reliably forecast the exact day or year when a particular fault will rupture. That reality applies equally to Cascadia. Moderate earthquakes occur regularly throughout the Pacific Northwest. Most remain isolated releases of accumulated stress along individual faults, rather than precursors to catastrophic megathrust earthquakes. Historical records illustrate this clearly. Over many decades, offshore Vancouver Island has experienced numerous earthquakes across the Explorer region, the Juan de Fuca Plate, and associated transform faults. Some exceeded magnitude 6, others formed earthquake swarms involving dozens or even hundreds of smaller events. Despite their frequency, the Cascadia megathrust has remained locked throughout this period. That does not imply these earthquakes lack importance. Each contributes valuable information regarding plate behavior. Repeated seismic activity helps researchers map previously unknown faults. It refines estimates of plate motion. It improves hazard assessments. It expands understanding of stress transfer throughout one of Earth's most complicated tectonic environments. The Explorer region also attracts scientific attention because of its proximity to active spreading centers. Along the Explorer Ridge, molten rock rises from Earth's mantle to create new oceanic crust. Although spreading occurs slowly, the ridge continuously manufactures fresh seafloor as tectonic plates gradually separate. Newly formed crust remains hot and relatively thin compared with older oceanic lithosphere farther away. As this crust cools over millions of years, it contracts, thickens, and becomes increasingly brittle. Fracture zones such as Sovanco intersect this evolving crust, providing long-lived pathways where tectonic stresses concentrate. The interaction between spreading ridges and transformed faults forms one of the defining characteristics of oceanic plate tectonics. Rather than existing as isolated structures, they function together as components of an integrated global system. The Pacific Ocean floor resembles an enormous conveyor belt. Fresh crust forms at spreading centers. It moves outward. Transform faults accommodate differences in plate motion. Eventually, portions descend into Earth's mantle at subduction zones. The earthquake southwest of Port McNeill represents one brief moment within that immense geological cycle. Its rupture likely lasted only several seconds, yet the tectonic forces responsible have been operating for millions of years and will continue long after modern civilization. Advances in marine geology have transformed scientific understanding of regions like the Sovanco Fracture Zone. Multi-beam sonar now reveals underwater landscapes with extraordinary detail. Researchers can identify fault scarps, volcanic cones, landslide deposits, and offset seafloor features once hidden beneath darkness. Autonomous underwater vehicles and remotely operated submarines allow direct observation of these geological structures. Rock samples collected from fracture zones reveal histories of repeated deformation. Sediment cores preserve evidence of ancient earthquakes. Magnetic surveys map the age and movement of oceanic crust. Gravity measurements expose density variations hidden deep below the seafloor. Together, these techniques provide a remarkably comprehensive picture of tectonic evolution. Yet even with these sophisticated tools, many questions remain unanswered. The Explorer plate continues to challenge traditional models of plate tectonics. Its precise boundaries remain topics of active scientific research. Some evidence suggests portions may be fragmenting into even smaller crustal blocks. Other studies indicate deformation distributed across broad regions rather than concentrated solely along major faults. Every new earthquake adds another data point, helping scientists evaluate these competing interpretations. The Pacific Northwest stands among the world's best instrumented tectonic regions. Thousands of seismic sensors continuously record tiny vibrations. High-precision satellite positioning systems measure crustal movement with millimeter-level accuracy. Ocean bottom instruments increasingly extend monitoring farther offshore. These technologies allow researchers to observe Earth's crust in ways unimaginable only a few decades ago. Even so, nature frequently reminds humanity of the immense complexity hidden beneath the ocean. The magnitude 5.6 earthquake southwest of Port McNeill illustrates precisely that lesson. Rather than representing a dramatic shift in regional tectonics, it serves as another expression of the continuous plate motions shaping Western North America. Stress accumulated, rocks failed, energy radiated outward. Then the fault locked once more, beginning another cycle of gradual strain accumulation. For coastal residents, preparedness remains far more important than speculation. Earthquakes cannot be prevented. Their exact timing cannot yet be predicted. What can be improved are resilient infrastructure, effective emergency planning, public education, and early warning systems capable of providing precious seconds before strong shaking arrives. Those efforts benefit communities regardless of whether the next earthquake occurs on the Sovanco Fracture Zone, within the Explorer plate, or someday along the Cascadia megathrust itself. Every earthquake serves as another reminder that Earth's surface remains in constant motion, even when that motion escapes everyday observation. The mountains of Vancouver Island, the rugged coastline of British Columbia, and the broad continental margin facing the Pacific all owe their existence to tectonic forces operating across immense spans of time. Long before human settlement, these forces sculpted the landscape. They continue doing so today. The offshore earthquake of the 20th day of July 2026 joins an extensive catalog documenting this ongoing geological evolution. Its magnitude drew attention. Its location sparked understandable questions about Cascadia. Yet the available seismic evidence points toward movement along the Sovanco Fracture Zone rather than rupture of the Cascadia Subduction Zone itself. That distinction underscores one of the most important lessons in modern Earth science. Not every offshore earthquake near Vancouver Island is a Cascadia earthquake. The northeastern Pacific contains an intricate network of active faults, spreading ridges, fracture zones, and small tectonic plates, each accommodating Earth's motion in different ways. Understanding which structure moved is essential for accurately assessing hazards and avoiding unnecessary alarm.